Hello, today I'm going to speak about nuclear magnetic resonance or NMR technology for groundwater investigations. Here is my table of contents. I will start from the introduction and introduce you to the physical principles of NMR. And then I'm going to switch to NMR technology and present you different tools that can be used in a variety of field applications. So what is nuclear magnetic resonance or NMR? So basically NMR is a non-invasive method to detect hydrogen. It is also applicable to other chemical elements, but hydrogen is the most concerned one for the groundwater applications and geophysics. And the NMR phenomena occurs when an isotope has a non-zero nuclear spin number, meaning an odd number of protons and or neutrons. So hydrogen atom has a single positive charge on it and it has a proton that is spinning. So it basically acts like a current loop and therefore has a dipole magnetic moment. A lot of other chemical elements do not have this property, but likely for us, hydrogen is the one that does have nuclear magnetic resonance phenomenon. So what we do with the magnetic resonance is that we detect a very small magnetic moment of the hydrogen proton. And this magnetic moment is so small that it cannot be detected from the signal hydrogen, and we must have a lot of hydrogens in our volume of investigation in order of millions or trillions in order to be that magnetic moment to be detected. Another thing about nuclear magnetic resonance is that there is a resonance phenomenon. In order to detect signal, we need to excite hydrogens at a certain frequency, which is directly proportional to the strength of the external magnetic field, B0, and this frequency is called Larmor frequency. It's this one. So the method is completely non-invasive. You don't need to touch anything. It's completely non-radioactive, and that's a common misconception about the technique since it has a word nuclear in that. So where does nuclear magnetic resonance used? So originally the method was developed in 1940s in organic chemistry, and until today is widely used in organic chemistry and pharmaceutical industries to characterize chemical bonds on molecular level. And these molecular bonds cause a different shifts in NMR frequency, and by using very large NMR spectrometers who has a very strong and uniform magnetic field, we can measure this frequency, these different frequencies, this shift in NMR frequency, and obtain NMR spectrum that can be used in order to define and characterize very complex organic molecules. Another common use of nuclear magnetic resonance is in medicine. So I guess everyone is familiar with MRI scanners, which is, in my opinion, the most powerful technology to diagnose diseases and injuries in human body, and MRI is based on nuclear magnetic resonance. And another use of nuclear magnetic resonance is in oil and gas industry and also geophysics and groundwater applications. So how does NMR work? So imagine we have some sort of the volume of investigation. We have grains of different sizes, and we have pores in between these grains, and these pores also have different sizes. So first thing that we need to have hydrogens. So let's imagine this volume of investigation is saturated with water. So water molecule has 2 hydrogen on that, and that's why it can be detected by the NMR. So in the absence of any magnetic field, these hydrogens will be randomly oriented in space. So the total nuclear magnetic moment will be equal to 0. In the presence of the magnetic field, like a compass needle tends to align in the direction of the North Pole, the same thing will happen with the hydrogens. They will then, when the hydrogen sense magnetic field, they will immediately align in the direction of the magnetic field, parallel to the main magnetic field, B0. So basically, the polarization of the hydrogens is happening as a first step. The second thing that needs to happen, we need to excite these hydrogens from their equilibrium, and that excitation should be done at the frequency which directly corresponds to the field of the magnetic field, the Larmor frequency. And you can see this equation here. So in order to do that, we used alternating magnetic field B1, which is applied at that Larmor frequency. And what it does, it transitions all the spins to the transverse plane, and all the spins immediately start to process about the B naught at Larmor frequency. And the final thing that needs to happen is the detection. So once we turn off that excitation field, that radio frequency pulse, the spins continue to process about the B naught field for some period of time, but in the end, spin tend to relax back to the equilibrium, which is parallel to the B naught field, and this precession creates additional alternating magnetic field, which is detected as a voltage on the detection coil. So it turns out that the initial amplitude of the NMR signal, which is shown here on the right plot, is directly proportional to the total amount of water in the volume of investigation. So it's basically the measure of the volumetric water content. And in case our formation is fully saturated, it's the direct measurement of the bulk porosity. So the NMR signal has an initial amplitude, but it also has some sort of decay. The signal decays over time. And this happens due to the fact that the spins, they do not have to rotate forever after we excite them, and they tend to get back to their equilibrium, which is parallel to the B naught field. And it turns out that the thing that governs that relaxation rate of the NMR signal is an interaction between individual water molecules in the pore and grain surfaces of the material. So for example, if you have a very large pores, like say gravel, the one that can be found in gravel, these interactions between water molecules do not happen very frequently, and this results in the very long relaxation of the NMR signal. So this plot will be very long. And if, for example, the water molecule is found in the very small pores, like Wilson clay, this relaxation decay will be very short. So these interactions between water molecules happen very quickly. So in geologic materials, we have a combination of large and small pores. There is no natural material that has the same size of pores. That's why that NMR signal decay will be a combination of the signal detected from the different pore sizes. So the shape of that NMR signal decay will be multi-exponential. As I mentioned before, water in the large pores will have a very long relaxation decay, and water in the very small pores will have a very short relaxation decay. So basically, from this multi-exponential signal decay plot, we can reflect the pore size distribution in our volume of investigation. So by integrating different parts of multi-exponential curve, we can characterize all water in the small pores and water in the large pores. So this measurement is not a direct measurement of bound and mobile water content. It's based on some lithology-dependent cutoffs and understanding when this happen in different types of materials. So basically, this T2 distribution is associated with the relative pore size distribution in our volume of investigation. And finally, we can use T2 distribution and also porosity to estimate hydraulic conductivity. And this estimation of hydraulic conductivity based on calibrated empirical models, which are lithology based, and provides a relationship between NMR signal and hydrology. How we estimate hydrological properties from NMR. So here I just wanted to show you the most common pulse sequence that used in NMR in order to measure the multi-exponential signal decay curve. And this pulse sequence is called CPMG. So what happens here is that we have a series of pulses. The first 90 degrees pulse is the excitation pulse. So basically that pulse excite the spins and transfer them to the perpendicular plane. And then after that we have a train of 180 degrees pulses. And we measure our signal in between these each two 180 pulses to obtain the multi-exponential signal decay curve, which is further used to estimate relative pore size distribution and also hydraulic conductivity. So the important parameters here to remember is the echo time, and echo time determines the shortest T2 relaxation time that can be detected in our measurement. And it also determines sampling density of decay curve. Okay, well, let's switch to geotechnical nuclear magnetic resonance instruments and start from the NMR borehole logging tools. So NMR borehole logging tools are known for many decades, and these tools are commonly used in oil and gas industries. However, of course, they are very expensive. They are operated by oil services companies, and they are very big. So these tools cannot be easily applicable for groundwater investigations. So this technology was optimized for near-surface applications relatively recently. And here on the right, you can see the comparison between oil and gas NMR tool and near-surface borehole logging NMR tool, which is a big difference between these two. So how does NMR borehole logging work? So remember, the first thing that we need to have a magnetic field, external magnetic field. So NMR borehole logging tools use permanent magnets in order to create that magnetic field, B0. So here you can see a schematics of NMR sensor. So you see the permanent magnets in the center, and these magnets are surrounded by transmit and receive coils, which are used to excite the hydrogens and also to detect the signal. So since permanent magnets are used in NMR borehole logging tools, we don't have a very uniform magnetic field as we move far away from the sensor. Instead, we have a magnetic field which is rapidly decrease as a distance from the center of the magnets. So we basically have sort of the radial magnetic field gradient as we move far away from the sensor. And in this case, we will have a stronger magnetic field closer to the sensor and weaker magnetic field as we move far away from the sensor. And of course, stronger magnetic field are associated with higher NMR frequency, and weaker magnetic field are associated with lower NMR frequencies. So in this way, we can tune our measurement to the particular frequency at certain distance from the sensor center. And in this case, the frequency 1 has a higher NMR frequencies and located closer to the sensor, and the frequency 2 has lower NMR frequencies and located more inside the formation. So once the frequency of operation is defined, the NMR data is collected in well-defined cylindrical shells. And these shells are located away from the zone of disturbance in the bore. So the measurement, we detect NMR signal, the water signal, only in this particular shell. So no signal is detected from in this disturbance zone or just within the well. So the NMR tool can be operated only in the open or plastic cased holes. These tools cannot be operated in the steel cased wells. It's because the NMR fields cannot penetrate the steel casing. And today a range of borehole logging tools exist on the market, and these tools can be used to log wells between 2 to 18 inch in diameter, and different tools has different diameters of investigations, so the measurement can be located past the annular space of the well, and the tool is selected based on the well construction. And also important thing to mention is that these tools usually operate using multiple frequencies, which are tuned below the AM broadcast band, and this basically the multi-frequency operation provides faster logging speed and also immunity to electromagnetic interferences. So data processing and interpretation. So the NMR signal is collected as a voltage on the detection coil. So before the NMR borehole logging tools are used in the field, they are calibrated in the big tanks filled with bulk water to detect 100% water content. And once the tools are calibrated, they have sort of like a calibration file which is used in the field to detect the actual water content, water signal in the formation itself. So here on the right you can see this average NMR signal which is detected along the well. So by looking on this result you can see that it's very different along the well. You do see some regions with high, very long signals, and in some regions it's much shorter signals. So this NMR signal is fed to multi-exponential function to obtain the T2 distribution plot, and this is a very informative plot. So you can basically differentiate between different different types of materials based on this T2 distribution plot, and basically have an idea about relative pore size distribution along the well. So for example, you can see that here you have kind of relaxation time of about 30 milliseconds, so it's probably some sort of the sealed, and maybe some fine soil can be found here. Here it's a very short relaxation times, so it's probably a lot of clay as well as in this region. And once you go here, you can see that relaxation time increases, so it's probably fine sand. And if you go to this region, is more medium-sized sand. And in this region, actually, you also see a very long relaxation time associated with a very large pore, so it's probably some gravel here in this region. And then, based on this plot, we can estimate bound and mobile water content, is shown here. And the final step is to estimate jelly conductivity by empirically derived formulas on the basis of NMR measured porosity and T2 distribution. So here's some specific example that used borehole NMR in groundwater resources application. And the history behind this work is that the old production well wasn't performing well, it wasn't producing enough yield, also was producing excess sand. And it also was defined that in this well, highest productivity was in the top of the well screen, and it was declining towards the bottom of the well. So it was decided to drill a new 16-inch diameter pilot borehole and use NMR to log it in order to produce continuous high-resolution log of aquifer properties. So, and these results can be shown here. You can see that actually the NMR log predicted that most of the production would come from this lower section of the well, and you can see that in this section longer relaxation times were detected, and this longer relaxation time indicated larger pore size distribution, which was also associated with higher hydraulic conductivity measurements. And next, the obtained NMR log was used to select zones for the following head percolation tests. And these zones are shown here on this hydraulic conductivity plot with these red lines. So once these tests were done, the results were used to calibrate the NMR-based hydraulic conductivity plot. And after that, the NMR estimated hydraulic conductivity plot was used to estimate NMR-derived specific capacity over final screened intervals. And it turned out that actually the NMR estimated well capacity was correlated really nicely with the actual well capacity after completion, as can be seen here. So another very wide use of NMR borehole logging technology is in environmental monitoring. So, and in this industry, the NMR borehole logging can provide reliable and accurate monitoring of very important hydrogeological properties in situ within existing PVC wells. NMR can be used to obtain soil moisture. It can be also used for high-resolution site characterization, and it can significantly improve conceptual site models of different sizes. And NMR can be also used to monitor different remediation processes in situ, and in this case the technology can be also used to conduct remote monitoring. And of course it can significantly improve project outcomes and reduce personnel exposure to radioactive materials at different sites. So here just some example of the study that was conducted at Moab Yumtra. And this site is a common uranium ore processing facility in Moab, Utah, on the edge of Colorado River. And here you can see just some logging results from two monitoring wells, MW2 and MW3, which you can see that located in very close distance to each other. However, NMR could provide very different hydrogeological properties within two wells. So later on, the NMR system was installed on that Moab Yumtra site and was used to monitor the change in NMR signal associated with the precipitation of the hydroxyapatite. So the formation was injected with solutions of calcium citrate and sodium phosphate, and the progression of this reaction was monitored for the period of almost 2 months with NMR technology that was controlled completely remotely. So you can see here that the NMR tools were installed in these two wells, and each tool was connected to its own winch, and the entire system was powered by batteries and that were charging using the solar energy. You can see solar panels here in the back. So during that period of time of 2 months, the NMR was capable to detect a huge change in hydraulic conductivity in one well, MW2, as can be seen here, between 2.5 and 3.5 meters, and also here at the bottom of the well. However, these changes in hydraulic conductivity was not as significant in the second well, and some smaller changes could be detected between 3.5 meters to 5 meters. Also, interesting to note here that the system was removed from this site due to the flooding in the area, but these two wells were monitored again in September 2023, and it was observed that that permeable reactive barrier, which is our hydroxyapatite, was stable over time. So it's this orange plot in hydraulic conductivity map here. Okay, so let's switch to the second family of NMR instruments and speak about portable and direct push NMR tools. So these tools are very portable and light. They are battery powered, and they can provide a very high resolution in situ NMR measurements, and they can provide vertical resolution as small as 2 inches. So these tools can be used in boreholes up to 10 centimeter in diameter and 60 meter deep, and they also can be used in combination with the direct push and CPT instrumentation, and provide very low impact and non-contaminated drilling waste. And these tools can be used in a variety of industries and provide very high resolution measurements of different hydrogeological properties. So here in the bottom you can see the results obtained from the direct push NMR tool. First of all, you can see the T2 distribution map, which is basically the relative porosity in the formation. So you can see that it's very different along the well. You can see that here it's a very short relaxation times associated with smaller pores like those in clay. If you move to this region, you have sort of kind of a peak with longer relaxation time. It's probably associated with well-sorted sand. And in this region, you have a very highly permeable region, and it's probably a lot of medium to large size sand. And then here is some sealed and well-sorted sand in this region. So these portable NMR tools, they basically use the same concept as the larger borehole logging NMR tools I showed you before. They just significantly smaller. They use smaller magnets, and that's why you see closer to the tool as compared to the previous larger borehole logging NMR tools. And these tools can be deployed using direct push method. So here, first of all, the drill rods are pushed into the ground, and then NMR tool is deployed through drill rods. And then once it's deployed, that expendable drill points is pushed out of the bottom of the rods, and this way NMR tool is exposed to the formation, and the NMR measurement is conducted on the way up. So here's a specific example of the direct push NMR logging that was used for high resolution site characterization, and this is the EB Island site in Washington State, and you can see that's a very high signal, very high quality data is observed using these tools. Here's the average NMR signal, which provides a very different signatures along depth, and you can basically differentiate between sealed with some organics and the very shallow subsurface here, which has a specific characteristics. It has a high porosity and longer relaxation time. And then you go to sort of a sealed layer, and then you have that medium to coarse sand with some gravel below it, and then you switch again to that sealed and end up with interbedded sand and sealed. So it's a very high resolution information that you can extract from the NMR measurement. And the important thing to mention here is that the NMR measurement can provide the estimation of the hydraulic conductivity up to 3,000 meters per day. And this is it's something that regular HPT tools are not capable of doing. So the limitation of the HPT technique is about 30 meters per day. So this is just HPT estimated hydraulic conductivity to compare with the NMR. So you see that the signatures are different. Just the HPT estimated hydraulic conductivity cannot provide, cannot differentiate, say, between coarse sand and gravel, like NMR can do. So here is another example of the direct push NMR used for high-resolution site characterization, and in this case it was used in Larned, Kansas to characterize aquifers on that site. And you can see that actually the NMR could differentiate between gravels and coarse sand very nicely in this case, and also could define that very low permeable zone with a lot of clay between 10.5 to 16.5 meters. And it also can measure the very high hydraulic conductivity values to differentiate between different types of materials. And this is something that HPT estimated hydraulic conductivity measurement could not do. So just to summarize this part of my talk, magnetic resonance logging technology can provide unique value for groundwater investigations. It can measure water content and porosity directly. It can provide robust estimation and other primary hydrological properties such as bound and effective porosity and hydraulic conductivity. The technology can be used in open or PVC cased holes, and it provides a very high vertical resolution and continuous log. And also the technology can be deployed by direct push equipment. However, you should remember that you should choose the tool where sensitive zones are outside of the drilling disturbed zone. So you should use the right size tool for your borehole applications. And don't forget that these multiple shells of investigation can increase logging speed and also identify radial variability and significantly increase your signal-to-noise ratio. Okay, so let's switch to the third family of products, which is surface NMR technology. So these tools are completely different from the borehole logging NMR tools I showed you before. So this technology is completely non-invasive, and it uses Earth magnetic field as a background binode field to polarize hydrogen spins. So the technology is completely non-invasive. You don't need to drill anything, and you can obtain quantitative measurements to estimate water content, porosity, and permeability of the subsurface. And the technology can be also used to conduct monitoring of subsurface changes and observe variations in groundwater level, groundwater infiltration, and other dynamic processes. So how does it work? So basically in the equilibrium state, we have an Earth magnetic field which polarizes hydrogen nuclei, and this Earth magnetic field is relatively small. It's about 50 microtesla. So the magnetization is directly proportional to the strength of the magnetic field. So usually very, very small signals are detected in this using this surface NMR method, and they order like hundreds of nanovolts can be detected. So the first state is the equilibrium state. Our hydrogens are parallel to the main magnetic field. So the next thing that we need to excite our spins. So and this is done by the application of the external magnetic field B1. And that B1 field is created by routing AC current loop through that surface loop wire, and by increasing the current on the loop, we can excite deeper and deeper groundwater. So yeah, once we have that excitation pulse, we transfer our magnetization toward the transverse plane. And the last step is the detection. So once that RF or excitation pulse is turned off, we will have some dead time, some delay before we can start measuring everything. And then after that excitation stops, the spins will start to process about B0 field to relax back to the equilibrium, and we detect that precession and relaxation properties of the spins. So here on the right you can see that smaller current, with smaller currents you can detect shallower water, but you will need to have a very large current in order to detect very significantly deeper groundwater. So data processing and interpretation. So here on the right you can see the raw data observed from the surface NMR measurement. So you can see the NMR signal is a function of increasing pulse moments or increasing current strength. And after we collect that data, some complex modeling should be done in order to specially invert the NMR signal and locate it in depth. So this is done by solving a set of linear equations to separate NMR signal contribution from each layer. And after we have it, we can use it to estimate decay time distribution and also estimate water content from these measurements, and also can use T2 distribution and water content to estimate porosity. To estimate the Jolly conductivity. So some limitations of this method. So this method is very sensitive to environmental noise. So then you do your measurement, you need to make sure that you are at certain distance from the power lines. It's very important to use noise reference coils in order to cancel some of the noise which is detected, and this is due to the fact that the NMR signal which is detected is very small. It's in order of hundreds of nanovolts, so it's very important to use noise cancellation schemes for these measurements. And here in the bottom you can see the signal in red, which is detected without any noise cancellation algorithms applied, and the blue plot is basically the signal after the noise cancellation. So it's a huge difference. Another caveat is that the technology is sensitive to magnetic geology. So in this case, more advanced pulse sequences such as SPINEC or CPMG can be used in order to resolve some water in the large pores. However, it's sometimes still very challenging, especially in case you have a very highly magnetic geology. And the depth of investigation surface NMR depends on the loop size. So the larger loop size you use, the deeper groundwater you can detect. And also it depends on the ability to generate and manage high voltage and current, and of course on the conductivity of the subsurface. So I would say with ideal experimental conditions, this technology can be sensitive up to 100 meters in depth. Okay, so here is some specific location that surface NMR was used to survey water well drilling locations in Chile. The history behind this work is that the company wanted first to make sure that they can detect water before we start drilling a well. So they used surface NMR and were able to detect water between 25 meters to 50 meters. So it's basically surface NMR basically increased certainty of finding groundwater and significantly reduced risk associated with drilling a dry well in this location. Here is another example that surface NMR was used to characterize alluvial aquifers, and this work was done in Crested Butte, Colorado. And The surface NMR measurement clearly indicated that second aquifer, which was sitting on the low permeable bedrock formation, and actually this second aquifer was unknown to the scientists who, and geoscientists who work in this area. So they were sort of very surprised to know that, yeah, that's a second aquifer here. And this second aquifer was also confirmed by more advanced surface NMR measurement, the CPMG measurement. So you can see two aquifers here between 2 to 6 meters, and this one was previously known. And this is the second one between 13 to 20 meters. Yeah, so it can be very, very useful. Surface NMR can be very useful to characterize alluvial aquifers in different regions. Okay, so let's switch to the final family of instruments and speak about NMR soil and core analyzer. The NMR soil and core analyzer can be seen here in the bottom. Then they look very similar to the small MRI scanners, and they are very useful for laboratory and also field measurements. You can identify hydrological properties from core and soil samples, and also drill cutting using this instrumentation, and significantly save your time estimating hydraulic conductivity and total and bound porosity of your core samples. So some specific applications of this technology is formation-specific calibration of NMR hydrogeological models, such as hydraulic conductivity. You can also estimate pseudo cutoffs for NMR borehole logging applications. And also you can estimate residual water content in the ore. So in general, since it's sort of a benchtop measurement, your signal to noise is very high, and you can use a very short echo spacing to characterize very short relaxation time associated with a very small pores using this method. So how does it work? So the technology again uses permanent magnets to create a uniform magnetic field in the center of the probe. So here, just the top view, you can see that all this formation, all this core sample senses the same magnetic field, which is associated with the same Larmor frequency. You can see that the signal coil is used as transmit and receive, and this coil creates excitation field which is perpendicular to the main magnetic field. So this is it. It's a very simple technology, but it can be very, very useful for the variety of applications. So here is a specific example that NMR soil and core analyzer was used to identify the effect of magnetic susceptibility on estimation of porosity. So in this study, multiple samples, each having different magnetic susceptibility values, were tested, and the main finding was that actually the analyzers that use lower magnetic field associated with the lower frequencies, lower NMR frequencies, capable to more accurately estimate porosity from the samples with high magnetic susceptibility. And also, it's also very important to use as short echo spacing as possible. So, the take-on from this study was that actually the borehole NMR tools that used low NMR frequencies can be used to sufficiently and more accurately estimate porosity in the formation that has high magnetic susceptibility. That use NMR soil and core analyzer to develop a methodology for determine the T2 cutoffs for solar samples. Different solar samples were provided from the lithium mining, and here just some pipeline that was used in order to identify these T2 cutoffs that later on were used in the borehole logging applications to more accurately estimate bound and mobile water contents. So here just a pipeline. You first measure your sample, you saturate it with some brine, and then you do your NMR measurement of the fully saturated core sample. Next, you do some gravimetric draining and weighting, and you redo your NMR measurement to obtain the difference in the NMR signal, and then you compare between saturated and drain NMR results to estimate basically these two T2 cutoffs. So just to summarize, hydrogeological NMR measurements provide unambiguous information on hydrogeological properties. It can provide direct detection and measurement of water in the formation. It can estimate porosity and relative precise distribution, estimate bound and mobile water fractions, and also estimate hydraulic conductivity and transmissivity. So NMR technology capable but not limited to characterize aquifer properties directly. It can be used to identify the most productive zones for screening and groundwater production. It can be used to characterize seasonal changes in the water table and used for soil moisture monitoring. It can be very effectively used for high-resolution site characterization and improve conceptual site models. It can be used to conduct efficient monitoring of remediation processes in situ and also within existing PVC wells. And of course, it can improve project outcomes and lower overall project costs. Thank you very much for your attention.